I'm going to tell you a little bit about C++. And most such talks are either about what the language is or how you use it. This I'm trying to make a talk about how the language became to be what it is. And it's the evolution from the early days up till about 3 years from now. And if I get a bit boring, you can look at the pictures. Essentially all of the pictures has something or other to do with C++. Like, what do you think those turbines have been programmed in? And so that's it. I am going to go a little bit into what is C++'s role in the world, what did I intend it to be, and what is it now. Then I'm going to give a code example. I really feel like a total fraud if I talk about programming and software development without showing code. I mean, if you see a presentation about software development without code, I start to worry. And then I'm going to talk about the recent evolution. A lot of the talk has to do with what has happened in the last minus 10 plus 3 years, something like that. And my thesis here is that the value of a programming language is the quality of the applications. What matters is what interesting things you do with it. That is my measure of success. Not how clever code I can fit into a dual column Pobble format. This is very much a practical exercise trying to do something good in the world. Of course you don't control what people are using the language for, and some of the things you might not like, but these are the things I consider somewhat cool. And I am not going to enter into language wars. I try not to be rude about C++ applications. So that said, you are not going to drag me into that. And there's lots of interesting stuff here. What I've been doing since my PhD days is distributed systems. And I'm still very interested in that, doing it. There is one of my notions of a distributed system. It's a distributed system with wheels. And a lot of C++ turns up in places where you would never think about it, and you will never see it if it works right. If you notice it's C++, it's probably because something went wrong. The point here is that nobody understands all of this. Nobody can understand in any depth all the applications that I was just flickering through a few pictures of. Neither do I. However, the purpose of the exercise, as far as I'm concerned, is to help people that are building these things. Therefore, if I built something that can only do what I can imagine, I've failed. You have to do things I couldn't possibly imagine. The group here has more ideas, more needs than I could imagine. And that's part of the point. So, what actually matters? The answer is lots of things. And one theme here is that we need stability and evolution. We need a language to evolve, our toolset to evolve, so that it can handle new things. The world is changing, we're changing, the challenges are changing, and the language has to do it. On the other hand, you've always seen languages that are really cool for about 5 years, then their designer gets a promotion and it dies. We can't have that. Not for things that last for decades. A lot of the things on my pictures have the interesting property that they were written 10, 15, 20 years ago. They are still being developed and changed. You have to handle that span. That's really hard. And obviously there's enough in this kind of stuff to talk for days. I have 1 hour. I'd like to point out that being the best at 1 or 2 things is not sufficient. I mean, that's how you can write a really nice paper. Nothing against academic papers. I read a lot of them. I have written a fair number of them. But that is not the end product for tool building. A tool is good enough if it is good enough for everything that somebody using it needs. Now, you have to remember that no language is good enough for everybody, and for everything. But if you should use a tool, it should be good enough at every aspect of what you're doing, not just being the best at something. And so let's go back and see what the world was like when I started. Photography was mostly black and white, it seems. That is a large computer. It's a PDP 1170. It allows a programmer to have 250 K of memory, and it runs with almost a megahertz, only almost. And this is Dennis Ritchie and Ken Thompson working on it. Notice the highly advanced I/O system. That was what the world looked like. And there's lots of things. C didn't have function prototypes. I hadn't invented them yet, so I didn't have them. Lint was the state of the art in static development. Yes, lots of languages has function, argument, checking, and conversion, but C didn't. There's all kinds of stuff. PDP 11s were cool, VT 100s. They didn't even have one. That's a teletype. One of the points is that everybody knew that object-oriented was useless. This is almost right, because 99% of people didn't know what object-oriented was, never heard of it, and of the ones that knew about it knew it wouldn't work. It was too slow, too special purpose, and too difficult for ordinary mortals to use. And I tried to convince somebody. He says, if you want a virtual function, you haven't done your analysis right. I mean, you want to call a function, you don't know which one it is? It's absurd. So there were some obstacles to overcome. I point this out because in retrospect, a lot of this looks trivial and easy. So I probably won't convince you, but it wasn't easy. So here's sort of a history chart as it relates to C++. Here is a line of development where the purpose of the exercise is to extract every single byte, every single cycle out of the machine. Starts with assembler machine code, go through BCPL and C, and then to C++. And up here we have the great improvement in programming, the greatest in history, which is basically somebody figured out that we should have human-oriented things, application-specific concepts in a language so that we can talk about our programs in the vocabulary we use when we design things, as opposed to looking at the machine all the time. And that's Fortran. And as soon as people had Fortran, the business people wanted one, they got COBOL, and everybody wanted one. And very soon we had about 20 of them, and had the net effect that everybody could write in a specific domain, much more pleasant than an assembler. However, they couldn't talk to each other. The terminology was different, the data formats were different, they couldn't even exchange data. So Simula here came about, together with object-oriented programming, as an attempt to say, why put application-specific concept into our programming language? Why don't we instead give the programmers the ability to design their own abstractions, their own concepts, their own types? And that's how we got object-oriented programming. And if you write in any programming language that calls a type a class, you can say thanks to Christian Nygaard there, because that's where it came from. Computer science was very new. He was trained as a mathematician. He knew what classes was. He did not know what types were. And so I needed something that could handle abstraction and could handle hardware, and that's why I built C++, by allowing abstraction mechanisms to be used there, and lots of interesting things happened after that. Now, C++ is, as far as I'm concerned, there so that I don't have to choose between elegance and efficiency. When I do things well, they are elegant and efficient. That is, when you express things really well, really clear, really logically consistent, hopefully the optimizer goes and generates really good code. That's the ideal, and sometimes we get it, don't get it all the time, and we can do even better. But that's the idea. And we do that by defining lightweight abstractions. Not big, heavy, complicated abstractions. They are relatively easy and you can do them in any language. But if you want a point and a matrix and a a complex number. It gets really quite difficult, and that's where the challenges are. And so C++ has been developed as a language for resource-constrained applications. There's lots of applications that you saw in those pictures, and lots of the stuff that I worked on, well, starting in the 80s and still today, where you could do much better if you had twice as much memory, or twice as many processors, or twice as fast processors, but you don't. Those server farms cost $60 million US, and if your code is half the speed of what it should be, you need to buy 2. And you have to power them up and run them and maintain them and all of this kind of stuff. So this is where resource constraints matters, and that means that C++ is deep, deep in our software infrastructure, because that's where you have the constraints of performance and reliability and all the other good stuff. And C++ offers a direct map to hardware and a zero overhead abstraction. Those are those 2 lines on the history chart. And again, no language is perfect for everything and everybody. And I don't know how many of you have read the Dragon book. It's a classical textbook in about how to build compilers. It shows the knight armed with the weapons of computer science, defeating the dragon of complexity. Sometimes the dragon wins. We haven't reached perfection. We can do much better. So here's what I mean by a direct map to hardware. The primitive operations map to instructions on the set. If you add 2 integers, it's the integer add operation. It seems simple, but a lot of languages don't do it. Memory is just a sequence of objects, quite often bytes, and you have addresses that can show which byte or which object you are talking about. That's it. It's a brilliantly simple abstraction that Dennis Ritchie made. You can compose objects with simple concatenation, like if you take some of the same type and put them next to each other, you get an array. If you put things that are of different types together, you can get structs and classes and things like that. And if you need to refer to something that's elsewhere, you have pointers that are simply machine addresses and sweet and sour sauce. So basically, this is the real secret of C and C++. It's really simple, it's really easy to map to the hardware, it's compact, it's efficient. Okay, so down by the hardware, life is actually rather unpleasant because there's not much help. And you don't really want to work with bytes and words and such all the time, and raw pointers and such. So we want to abstract from it. And so the basic idea of C++ is that it should allow you to build your own types. And they should follow what I call the zero overhead principle. What you don't use, you don't pay for, and what you do use, you shouldn't be able to hand code any better. So if I'm providing a notion of a class, you should not be able to hand code it with pointers and structs and such that does anything better. And there's lots of examples here. And finally, sometimes we don't actually need to generate any code, we just compute the answer at compile time. That's getting more and more popular. So here, it's abstractions all the way down. We start with our high-level abstractions, and they build on lower-level abstractions. They build on the language, which builds on the basic machine model, and the machine model is also an abstraction. Of course, there is much more to machine architecture than that. There's caches and all kinds of stuff like that. This is an abstraction. This is Dennis's abstraction. It's a good one. I borrowed it. And you go down, you get to the hardware, and what do you find? No, an Intel machine does not execute 86 instructions directly. It translates 86 instructions into a much nicer instruction set, which it can optimize and execute better. It's abstractions all the way down, hence the turtles. And you always have to abstract from concrete examples. There are people who think abstraction is another word for bloat. This is not the case if you do it right. You abstract from concrete examples, maintaining performance all the way up. And you have to keep simple things simple, because sometimes when you abstract things so that it can do everything, you can do nothing simply. You want simple things to be simple. These are sort of design principles that I've worked with over the years. And then there's this question of naming. How did C++ get to be called C++? Well, there was a language here called CPL. It initially stood for Cambridge Programming Language, then they ran out of money. They combined with Imperial, and then was combined programming language, and then it was too complicated, they couldn't build it, and it died. Except they built a simple thing, Martin Richards built a simple thing called Basic CPL at MIT actually, and then it became B for a short while, and then C was Dennis's work that made it efficient and better for hardware use, and then C will classes, as it was called, for about 3 years till I was told I couldn't call it C will classes because some people were calling C old C, and that was supposed to be rude to Dennis. I was not rude to Dennis. I had lunch with him most days, and we never had a harsh word between us. Then I tried to call it C84. That never flew because the people from the C committee came and said, well, please don't do that, Bjarne. It would really be embarrassing if a superset of C85, the standard C, would be a superset of C85. Anyway, they didn't finish till 89, but anyway, that was not. So I had a competition for calling it something, and C++ won. As I said, we knew ++C was semantically better, but that was too much of a joke. So what is Strachey doing up there? The answer was he was the main designer of CPL. And it didn't matter whether it was Cambridge or combined, because everybody knew it stood for Christopher. So you still got it there. I should point out, that's Murray Hill where I worked and where I designed C++ right over there, and that's Cambridge, part of it. So, what features does C++ offer? Well, we had a competition a couple of years ago for what is your favorite C++ feature. And when Roger Orr suggested the end curly, we all backed off. That can't be beat. That's it. That's where all the magic happens. So one of the things that distinguishes C++ over the years is this model. You make objects with constructors. And if you don't say anything else, they're in a scope. And at the end of the scope, the destructor fires, doing the magic, cleaning up the messes, closing up what should be closed up. That's the really key. And I looked at my notes, and it's a real core of C++. It came in the first 2 weeks of development back in '79, together with classes, member functions, information hiding, function declarations, and other good stuff like that. And basically that is the key to a lot of what we are doing today. The standard library uses it, the error handling is depending critically on it. So what is it? Here's a type, a user-defined type, a class. It has two parts, the public interface and the implementation. So basically this is one level of abstraction, and that is a lower level of abstraction on which it is built, and you work that up and down all the way. And I have given it, there's an element type, and you can construct this one by a list of initializers of its element type. And here is the cleanup function. That's where you release the memory you do. So here we can use it. I take a vector of doubles with some well-known constants, and I take a vector of strings with some well-known language designers. I would like to point out I've been using this slide for years. I did not put it in to grease you. This is the way I do it. And basically, we get to the end curly here. It goes and cleans up everything that was created by the objects in that scope. And that's a very powerful abstraction mechanism. So we use it for just about everything in the C++ standard library. There's vectors, lists, maps, hash tables, strings, and such. They're all working on this model. You acquire resources when you create a variable, and you release it again at the end of the scope. And these are things that we acquire. It's not just memory. There's things like thread handles, file handles, buffer capacities for streams, locks, and when we have smart pointers, we do use counts and things like that. This means that if you can't just fire up a garbage collector and collect all the memory, not only would that give you longer resource retention, because instead of cleaning up the mess, you leave the mess for somebody else to clean up later, therefore the resource is held on for much longer. Some experiments shows on average twice. Anyway, and this works recursively, so if I have something like a gadget which holds a file handle and a lock and such, and a vector of records that contains, it all works recursively. It works all the way. Okay, so let's take a more concrete example, semi-concrete. There's a gadget I created with some initializer, and I get a pointer out there. This is the way we wrote code in the 80s. This is the way they wrote code in Simula in the 60s. There's nothing new here, and we're seeing too much of it. But anyway, this is what we do. We don't actually know what this one does. Its constructor grabs all the resources necessary for working well, and now it's ready to use. And we go down here, and if there's X is there, we throw something. If X is that, we return. And when we are finished, we delete the object again. I mean, we acquire using a new, we delete, we release versus using a delete. However, as you see, sometimes we don't get there. So people scream we want garbage collection because this is easy to forget, it's easy to get wrong. It's particular if we throw, we don't get there, if we return, we don't get there. So this leaks. And so it comes that you don't really want news sitting out there naked, and you don't want deletes being there naked because they correlate very strongly with bugs. So we want to get rid of it. There's an easy way of getting rid of it, is that instead of having the gadget made by new, we have a function in the standard library called makeShared. It makes an object of that type with that initializer and return a shared pointer. A shared pointer is a counted pointer. When the last shared pointer to an object is destroyed, the use count has gone to 0, it destroys an object it owned, and therefore we will have the gadget destroyed there, there, and there, and the problem goes away. Except that now we have shared pointers, and we have use counts, and this violates the zero overhead principle because we have to access that use count, update and release it in a multi-threaded environment. That is actually a costly operation because it has to be synchronized. And anyway, I don't want to create garbage. I can't see any garbage here that needs to be collected. I can't see anything that requires a use count. I have one pointer and it goes away. Why do I have to count? 0, 1, 0. No, we can do better. Actually, the simpler code is there. You just take a local variable, control it, and you use it, and the destructor will be called there, there, and there, because when you go out of scope, the destructor is called. Problem solved. And the code is shorter, and so don't use new in general code because they belong in resource management code. So if I see a delete in your code, I assume there's a bug, that you have too few or too many deletes. And if I see a new, I know you need a delete somewhere, so I assume there's a bug in your code. So this is much simpler. And if you really need pointers that needs to be counted, you don't know about ownership, yeah, share pointer is there. It's actually quite useful, but people overuse it. So this leaves us with one problem. That is, quite often we make a big object, so lots of data. And then we want it to get out of the function that did it, get back to whoever requested it. And this is what people use pointers for, and they use free store, also known as dynamic memory or heap. They use to that, and then they send a pointer back, and now they have all the problems back again. So we need to avoid that. So here I make the gadget, and here I return it. And conventionally, when we return something, there's a copy. So basically here I call F, and here we copy the G out to GG. Now I must point out that only a computer scientist could have thought of that. So to get this one from here to there, you make a copy over there and you destroy your original. No. babies about 4 to 6 months old know, here it is, now it's over there, now it's back again. They can figure it out. So we just have to make sure that that's what we do. So here is G, it's a gadget, and if it's a big thing, like a matrix, a vector, a collection of stuff, the stuff will be over here somewhere on the free store, and this is a handle to it. So all we need to do is to copy the handle into GG, and the handle is small. If this was a matrix, it would probably be 2 words. If it's a vector, it's 3 words. And then we cut the connection to the first gadget so that the destructor doesn't get to throw away the good stuff. And problem solved. And so the cost of getting, say, a megabyte of stuff out, if you do it like this, is, well, 2 to 4 memory assignments. And now you no longer have to worry about pointers and memory management or shared pointers and all of this stuff. This completes the control of the life cycle of objects. Now, some of us have been doing this since the 90s, but it's only became systematic and guaranteed that it could be done in the in C++ 11. This is the handiwork of a guy called Howard Hinand that found out how to formalize that. So that's easily done now. Also, I'd like, when we talk about evolution, to point out that I have never claimed C++ is an object-oriented language. It never was just an object-oriented language. It was never meant to be just an object-oriented language. I don't think everything should be in class hierarchies or any of that stuff. So C++ is not object-oriented, just object-oriented for any definition of object-oriented. For starters, we need to deal with this direct mapping to hardware, and hardware tends to be messy, so we have to do things that doesn't behave like objects in a real way. They're actually real-world objects, and you have to obey their curious and somewhat perverse semantics. So we deal with this. Furthermore, we want value semantics for some things. So A becomes B means that they have the same value, and modification of the one doesn't fix the other. This is what we do for integers, for complex numbers, for points, for vectors, etc. So that model has always been in C++, and it's one of the things we do. Also, I want to say square root of 2, not 2 dot squirt. I really think this is the nicest notation, this is the nicest notation and such, and I don't want to have 2 versions of things. If I add a floating point number to an integer, I don't want the integer class to have something that takes floating point numbers and the floating point number class takes something that takes integers. I want the old-fashioned, like 300 years old, notations that it. Furthermore, generic programming was always part of the C++ plan, so that doesn't fit with the object-oriented thing. So these days, the control of C++ is by an ISO standards committee. And the way that happened was that representatives from HP and Sun turned up in my office and explained to me that I wanted to standardize C++ with ISO. And I said, well, it's not ready, it's not finished, it's still a project, and they sort of twisted my arm, ow, ow, ow. And in the end, I said yes. The argument was that you could not have a language, major language supported by, controlled by a single company. Everybody believed that in those days. It has been proven untrue. People are using Java and C#, even though they're owned and operated by an individual company that might be your competitor. Anyway, at the time, nobody believes that could be done. They had not thought about the advertising campaigns that could do it. And the other argument was rather blunt. Well, we will not trust your employer, AT&T. We will, of course, trust you, but you could get run over by a bus. End of quote. So I agreed to standardization. There's many kinds of standardization. The ISO standardization here is sort of the gold standard of standardization. It's thorough, it's open, and they have some rules. And so we get long-term stability, which is a feature, an important feature to many of the major users. It's vendor neutral. It's really hard to sort of juggle the C++ definition so that it favors my company rather than yours and such. And there are dangers. Design by committee is horrible. Stagnation could happen if people decided not to do major things because they couldn't agree on which major things to do. There is divergent direction of design. If you get sufficient number of people, they can't agree on anything. And they have a tendency of over-elaborating any individual feature. You can see that in C++ in places. I'm not going to go into detail. I'm just going to show you the picture of the committee. So this is what it looked like. Then it became that, then it became that, and this was earlier this year. How do you get that group of people to agree of anything? They come from different countries, different industries, have different philosophies, have had different education. This is really, really hard. And I reckon this is a picture of my major problem with C++ today. It is amazing that we have succeeded as far as we do, but let's see. I'm going to talk the rest of the time how we got from, well, about there till 20 years from now, to 3 years from now. So there's the evolution. We got a new standard in 11. The first one was in 98, then 14, then 17. C++ 11 was a major improvement. This was what we had learned over the previous decade and a bit. Standards usually come every 10 years. We actually took 13, which was one of the reasons we decided we can't keep on doing this. So we decided we were going to go on a 3-year cycle and deliver what we had to deliver. There's lots of new features in 11, lots of simplification. One of the ways I'm working is that there's a language, we can't take things away because of stability. How can you make it simpler to use? And the answer is have features that are simpler to use than the general ones, and then have rules for how to use them well. Now, people say, why don't you just throw away the old stuff? Well, half of the pictures I had in the first 2 slides would break, and everybody wants 2 more features, and by the way, the language is too big, you should make it smaller, and don't break my code. These are the sort of the hard constraints on evolution. And we have technical specifications and such. Now, we have 3 major implementers of C++, Clang, GCC, and Microsoft. And by the way, they shipped essentially all of C++ 17 this year. And the standard hasn't been signed off in Geneva yet. The technical guys have done it, and the technical guys have delivered the compilers. A lot of you will be using them already. We are delivering on time. This is spectacular for the group. I mean, remember? We delivered on time. Not as much as I would like, but we delivered. So C++ 11, 10 years of experience, long list. You can look up the lists. The Wikipedia has some CPP reference. There's lots of places. I am not going to go into details. Going through this slide in any detail will take a day, so we're not going to do that. I'm just going to show one example here of C++ 11. So here I'm going to say the old problem. In a container C, I want to find all the elements that has the value v. And what I'm going to do is I'm going to return a pointer to each of those elements. And let's see an example here. We have a string. A string is a container of characters. Mary had a little lamb here. And so for each pointer that comes out of find all as a result, by giving it m and looking for the a's, I'm going to see if the pointer really points to an a. If it doesn't, there's something seriously wrong. Okay, so in other words, I want this to test whether that was an a, that was an a, that was an a, and that was an a. The way we do it is we start a vector of pointers to elements. In this case, the value type of C is character, char. And for each x in C, see if the value is right. If it is, push the pointer to the end of the result vector and return the vector. Now, if this had been a C++ 98 program, we would have had a serious performance bug there, because I mean, a vector of 4 elements is not that expensive to parse. However, I might have given it a megabyte of data and returned 1 million pointers. And even modern hardware can feel copying 1 million pointers. However, modern vectors do not copy, they move. So that is dirt cheap. So the difference between C++ 11 and C++ 98 here is what you don't see. You don't see any pointers, you don't see any allocations, you don't see any range checks. It's all gone away. It's done implicitly in places, and it's done efficiently. So that's what's different. So for 14, we finished 11. So the point here is that when you have a large project, before the end of the project, before the shipping date, you have a feature freeze. And while the feature freeze happens, you learn things and you can't do anything about it. So for a standard, the feature freeze is about a year before you ship the standard. After having a major release, you start using it and you learn things you hadn't guessed. And so the idea is after 3 years, we have had the feature freeze, we have learned what the effect of the use of the features are, and we can fix it in time before the next feature freeze. And that's how we got C++ 14. It completes 11, that was all planned, and it has lots of little things. There's here, for instance, the graphical people really wanted binary constants, so we gave them binary constants. OB means it's a bit pattern. Then we found that people can't read this stuff. Can you see what that is? Okay, then we gave people digit separators, which are just for the humans reading the code. We're always interested in things that simplify things by making bugs less likely, and that's what this does. Lots of things here. Remember, we are still maintaining compatibility and stability. Yes, we would like to get rid of some of the old crud, but we can't. We've tried. So one of the things we've been doing in the late framework, we had a lot of requests for being able to do more at compile time. So a lot of people do the following. They have some code and they need a value in there. So they go to a doodle pad on the side and they calculate it, or they use their calculator and they get a value and they put it into their code. Then you wait a couple of years and it's now the wrong value. And you have a magic constant in your code and you have bugs. So we had requests, especially from the embedded systems industry, for doing better things at compile time. They also sometimes want to put constants into ROM, and C++ wasn't good enough for that. Actually, I think it was, but they didn't agree. So here is an example. Somebody in the Japanese embedded systems industry wanted an integer square root function to be executed at compile time. So we do that. We say that we want to have it so that it can be calculated at compile time. Then we write the simplest algorithm we can find. This will be executed at compile time. The compiler executes it. To be able to do this trick, the function has to be pure in the sense that it cannot have side effects and it cannot operate on any data that isn't its arguments. If somebody likes nice mathematical functions, just require their const expr. That takes care of that problem. Furthermore, it allows the compiler to squirrel away the information necessary to do this, and if it did it for every function, you couldn't compile really big programs. So it's important that we have to say it. So we can now take the square root of 9 and take the square root of 1, 2, 3, 4. And we don't have to use a doodle pad, and we don't have to do strange things with macros to do it. Now, C++ is supposed to do the basic stuff and then to handle abstractions. So let's see. We can do compile time abstractions. Here's a little abstraction. It's a weekday of June the 21st, 2016. This is an example of the use of my favorite date library. This is very nice, and it writes Tuesday. We can do that at compile time. Let's take a static assert, which is an assert that is evaluated at compile time to see if it works. So I'm saying that the weekday of June the 21st, 2016 is a Tuesday. And it is. So this assertion does not fire. But if I had been wrong, it would have given me a compile time error. So we can actually do non-trivial computations at compile time. By the way, this library is more efficient than anything else you've done for dates. So it has not become elegant by being inefficient. So 17 should have been a major release. The idea was to pick up the Intel idea of tick-tock, tick-tock, major release, minor release, major release, and C++ isn't, 17 isn't. So if you hear me grumping about the standards committee and the slow rate of evolution of C++ and the many little features, this is what I mean. This should have been great, it's only okay. That is, there are a little bit for everybody. I think everybody will find something they like. The problem is that there are maybe 80 different features, and if you like 2 of them, you still might have to understand the rest of them. There's a nice parallelism library, there's a variant type that's useful, some way of dealing with multiple return values and such. This is good, but it's not great. So let's see, where do we go from here? And we need a guiding philosophy for kind of this. We can't just say, is this feature good? Let's take it. Is this feature good? No, let's not take it. What are the criteria? What are the direction for where we're going? So basically my aims include complete type and resource safety, as fast or faster than anything else, good on modern hardware, whatever modern hardware is going to become, and significantly faster compilation, even though we are doing better checking. I don't think that's a modest aim. And basically, dream no little dreams, that's his slogan. And the best is the enemy of good, that's his slogan. I can't just dream. We're going to build something, it's going to be useful. I want this to be useful in 2020, and I want the prototypes to be usable next year. So we're going to do that. That's an engineer, right? So make C++ a much better tool for building demanding applications. That is the ultimate aim, and these are the sort of more specific aims, the challenges I try to set the committee with the science. So why philosophy? The people say, I don't want philosophy. Philosophers are, no, anyway. So it is absolutely the only way of maintaining a direction and to have a coherent language. This is absolutely essential. And it's more, a language is more than a collection of features. An individual feature can be great and just be a distraction in the context of a type system and other features. We must do better. We must have a balance of features. And basically, we don't want to have mere habit. And the design rules are mostly non-technical. And this is where it's hard to get through to the geeks. I actually wrote up some design criteria in the early days, and here's from a book I wrote about it, The Design and Evolution of C++. If you want to know about the early evolution of C++, you can read that book. And I wrote 2 papers for the History of Programming Languages conference, which you can find on my publication page, that also describes evolution. It's all of these features I'm skipping over fast here, because I only got an hour. But basically, drive by real problems. I think theory is great for solving a problem once you have decided that it needs to be solved. I think theory is a lousy guide to what should be done. And so don't have a sterile quest for perfection. If I can come up with a 99% solution, I'm not going to wait 2 years, 3 years, a decade for the last percent. And so there's things like this. You can read this for details. And I'd like to point out 2 of the things documented in 94, and actually I could probably document them for 84 or before. No implicit violation of the static type system. Now, this surprises people who are used to C and such, and even parts of C++. But there's a difference between ideals and what you can get. I'm going to get this one, sooner or later, but I haven't got it yet. Dennis Ritchie said C++ is a strongly typed programming language with weak enforcement. Very weak. But the underlying system is sane, except possibly for some conversions that go both ways. And anyway, I really want to eliminate the preprocessor. So still trying to do that. It's really hard. There's people who've got a million lines of code and says, oh, you're telling me to get rid of the macros? Yeah, I'm telling you to get rid of the macros. And they laugh. But I actually think we're going to get rid of the macros in something like the Windows kernel. It's probably the worst macro hell on earth. And that is why they have decided they actually agree with me, because that hell is what they've been living in for a while. We are going to make progress, but remember, this was early things. We are still working on it. So what do we want? I want a major release in 20, C++ 20. My definition of major is it's something that changes the way you think about programming, the way you think about building systems. That's the definition of major. Minor is everything else. And what can we get? I like science fiction, but I don't like to talk science fiction. Everything on this slide actually has been implemented somewhere. So it's all very mild science fiction. And by the way, that is a show-off slide. I thought it was very cool when I learned that Douglas Adams was programming in C++. And so this video game was written in C++. So I want concepts, which basically is constraint generics. I want modules, faster and more hygienic compilations, coroutines, contracts. I didn't know it, but when I wrote this slide, but last week I was told that the implementation has started in a university in Spain. Static reflection, there's a problem. We have 3 designs, 3 with implementations, and now you have to have the committee to decide which one to have. And I really, really want them not to have the union of those 3 designs. So that's what that question mark was for. Networking, we have a really nice networking library, close to optimal in many ways in widespread production use. Better parallel algorithms, better futures. We have the model of promises and futures for sending information from one thread to another without having explicit locking and all of that stuff. We have it, and it should be much better because there's some design errors in the C++ 11 design. And I want a new standard library with the concepts here so that we get proper type checking. Let's see how we do it. If you go back and look at my very early papers from 81 or thereabouts, you'll see I wanted object-oriented programming as pioneered by Simula, and I wanted generic programming because basically I wanted a vector of t's where t was something I could specify as a parameter. And once you have vectors of t's, you want a sort of t, what sort of vector of t, so you have parameters for data structures, you have parameters for algorithms, for functions. You need both. Okay, so I conjectured that you could use macros for that. That did not scale. Macros for generics works for about 2 people, not much more, and it's unmaintainable. So in 87, I made a design of templates. I wanted extremely general and flexible. I always want that. I want 0 overhead. I always want that. So basically, I wanted something that could do more than I imagined and could compete with C arrays and other basic C facilities there. And of course, I wanted well-defined, well-specified interfaces because that's good and that's what we always want. And 2 out of 3 ain't bad. I could not do that. I don't think anybody in the mid-80s could do all 3. If you look at other languages that has things like that, they don't have both, all 3. So we can now do it. The way we do it is, let's see. The problem was that we got compile time duck typing, and it gets very, very complicated and horrendous error messages if you get it wrong. And it was very, very successful because of its nice features, flexibility, performance, etc. We're trying to address this complexity by providing const expr functions that can be evaluated at compile time, so you can do metaprogramming that is not template metaprogramming. If the result of a compile time computation is a value like 7, you want to call a function to get it. And we want to specify interfaces. So here is an example of something using concepts. I want to sort something, and I want to sort anything that's sortable. There's a definition of what's sortable somewhere. You can look it up in the manual, in the standard. It's something that is a sequence with a beginning and the end, and it has elements. It has a less than operator, and it has random access to the elements. That's it. So anyway, if I have one of those, I can sort it. As it happens in the standard, you can't sort a list this way, because a list doesn't have random access to its elements. So the way you do it is you just copy the list into a vector, sort it, and copy it back again. That's usually the most efficient way of doing a sort of a list. Now, I can then say sort a vector, and it says, does a vector have all the properties required to be sortable? Yep, so we can call it. We can sort the list. Does the list have all the properties that is required to be sortable? No. Let's try this one, and the answer is yes, and we just do it. And notice I am not saying that a sequence is less than sortable or something like that. I'm just trying to see what works, and there's a very simple overloading rule. If you match one thing, that's it. If you match two things, if the one is a subset of the other, you pick the largest. End of rules. So that works nicely, and you can specify your requirements like this. Here's a sequence. It requires that the type has an iterator, that there's a beginning and an end, and they have an iterator, and those iterators are actually iterators, not just called iterators. End of story. And concept sortable means that it's a sequence with random access with the ordered value type. That was just what I said. This is terser than English. So that works. By the way, it's shipping in GCC 6 point and higher, also 7. So this is not really science fiction. Modules is another thing we're working on. Compilation just takes too long in C++. We have the include model. It includes all the text. You get a whole lot of text, and the compiler deals with it. Compilers are superb at compiling a lot of text, but it still takes forever. So we want to do better. We want to define modules. Here I'm defining a module called a map printer. And the map printer, to implement that, I need IO streams, I need containers, and I want to use namespace std. Notice I'm saying import, not include. And it exports something. The idea is that when you include, you get what is exported. And the module itself is a semi-compiled construct that is self-contained, semi-compiled once, and then expanded where necessary, and that is very significantly faster than includes. I have seen real live examples that compiles 10 times faster. So we're going for factors here. If I get 5 times, I will be happy. If I get 10 times, I'll get even happier. If you give me 40%, I'll be sad. This is ambitious. And so here I am going to export a template that prints maps. It takes a sequence, and the sequence has to have printable value type, key types, and a printable value type. And then I do for all key value pairs in M, print them out. Now, I want this to work in C++ 20. This works today. It's called structured bindings. It's part of C++ 17. This works in the Microsoft implementation, and the concept works in GCC. When I first wrote this slide, this worked only in Clang. You can see why I want a standard. I want all 3 in all platforms I'm using. Standards are really useful. So how are we going to evolve? The language is getting bigger and more complicated, and the users are more busy than ever. So what I want to do is to answer the question, how would you like your code to look like in 5 years' time? And if you think very much like today, I think you're unambitious. We can do much better. So I'm doing it, attacking with sort of a drug cocktail through language design, coding rules, a library, and some static analysis. And I'm after type and resource safety. And I want to eliminate over-complex techniques by analyzing the complexity and throwing things out if they correlate with bugs. And so basically, this is the holy grail I'm after. There's a project called the C++ Core Guidelines, which is a joint project. You can find the current guidelines on GitHub. It's a joint project between Morgan Stanley, Microsoft, Red Hat, Facebook, and a lot of others which you can look up in the contributor list on GitHub. I encourage you to note Microsoft and Red Hat. There's not many joint projects between those two organizations. I think we're seeing progress here. Anyway, so what I want, it uses the guidelines, and then it has a support library. By small, I mean about a dozen abstractions, simple ones, and I want static analysis. That is work in progress. So I can write type and resource safe C++, but I want it guaranteed. And we're working on those guarantees. But basically, no leaks, no memory corruption, no garbage collector, by the simple trick of not having any garbage. No limitations on expressibility. I don't want things safe by making sure you don't say anything interesting. It's still C++. No performance degradation, so we can't just test things at runtime. Still ISO C++. I don't want to design a new programming language. It takes forever to build. It takes forever to get deployed. Basically, the minimum penalty for designing a programming language that works is 10 years of manual labor, meaning you have to work on the manual for 10 years. And I want it tool enforced. And so basically I want to get rid of code like this. Here is innocent looking code. There's code with a delete in it. There's a new, I call a function and I use it. This is disaster, because by the time you get down there, the object doesn't exist anymore. So this one either reads some memory, which is not the object that the pointer used to point to. It may actually write your favorite data structure, and you have the most mysterious bugs you get. The problem with dangling pointers and their use is you can't see them. That's why I chose this picture of a nightmare. Never let a pointer outlive the object it points to. Easy to say, hard to scale. I mean, Dennis said it. It's been there forever. Okay, so once you get rid of that one, there's other bugs. Unions, cast, null pointer dereferences. We can do all of that. This monster is less dangerous. You can see him. And you can drain his pond and your home. Okay. Just to show this is not science fiction, there is a printout from the from Visual Studio last year. I have a struct there that contains 2 pointers. I make one of them here in the analyzer objects, because I'm throwing away the information that there was a new. Once it's up here, the information is gone. Therefore, we have a potential leak, and it will not like it. So we're deploying this kind of stuff now. And basically, there's a lot of challenges left. I didn't say C++ was a perfect language, never have. I doubt I ever will. There's lots of challenges left. The world is changing. We must do better. I mean, our civilization depends on software. I mean, if our software really broke, we will end up starving. This is not an exaggeration. We have to do better than what we're doing, and it has to be done on an industrial scale, and staying coherent is hard. And so I reached my limit here, and we have time for a few questions.